Okay, so thank you for this nice introduction. So I'm going to present our paper with Lara Rad from Montevideo, who is present here with me, and José Lezama, also from Montevideo originally, and not doing research, and Jean-Michel Morel, professor in Hong Kong. Well, so our work is about painting style transfer. So what is this? The motivation for this task, I'm sure many of you know, but it's to transfer the style of a painting to a classical image, a picture from a camera. Okay, so this is actually a highly nonlinear transformation, and it's actually very ill-defined and quite subjective. And in the presentation, I'll speak about the content image for the original picture, and for the painting, I'll speak of the style image. Okay, and by reproducing deep neural statistics, there was a paper by Gattis, Ecker, and Bedge from Germany in 2016 that was really a breakthrough, and actually it opened a new research field called neural style transfer. And you have examples of the original paper. But let's, first, before looking at synthesized images, let us look at a real picture received by Van Gogh. And when you go in a museum and you see such a picture, okay, you see it like that from far away, and what you do, well, you can come closer, okay? And you see now the amount of work from this picture, okay? And if you come closer and closer, you see the many brush strokes, the different colors, and here, for example, you can see that Van Gogh even let some canvas raw without paint and played with it. Okay, so you have a very different amount of details. So our claim is that actually ultra high resolution is really critical to convey the complexity of a painting, because you have composition, color palette, and then brush strokes, paint textures, and then canvas texture, and tiny cracks into the paint. Okay, and this is actually the thing we would like to reproduce in a style transfer. Okay, so our motivation today is to produce the highest quality style transfer for really ultra high resolution images. And when I mean ultra high resolution, I mean larger than 4K, so larger than this screen. So I do some close-up several times to convince you. Okay, so let me just first recall the original algorithm by Gattis and co-authors. So what did they do is they proposed to use the CNN features from the VGG19 we already speak about today. And the VGG19 features will be used in two ways. So first we will put the image through the network and extract at some layers, some selecting layers. So you have typically 5 layers within the hierarchy. And either you will keep the features to have a spatial information, or you will do some spatial statistics through a gram matrix. And so the gram matrix is that you take all the features and you do the average of the feature with a certain number of channels times the transpose of these features. Okay. And so there is no spatial information here. It's just a statistics of correlation. And this is what they propose. To the style transfer is performed by optimizing style transfer loss. So you have the content image U, the style image V, and you optimize a transfer loss that has two terms. The content, so the content is just a mean square error between some VGG features at some layers, and the style is a mean square error, but between gram matrices. So this is some spatial statistics at different layers. Typically we use 5 layers in the VGG hierarchy. All right. So when you do this, you have the result I showed you in the first slide. And actually, the transfer is already limited by the architecture of the VGG19 due to a finite receptive field. And typically, if you have images larger than 500 pixels, you should also apply a coarse-to-fine approach, which is quite standard when you do texture synthesis. So you first downscale the images, apply the style transfer, and then upscale the results to initialize the transfer at the next scale. Okay. And when you do that, you're able to do kind of high resolution transfer that is way different from the high resolution image. Whereas if you do just the style transfer at the high resolution, you get not so much of transfer. Right, but then it's still limited to 3000 pixels in resolution. because actually computing the VGG features of a large image is really memory consuming. All right. So just bypassing by, for this work, we also use not just the ground matrices, but a small correction with the mean of the features and the standard deviation of the features, just to correct some loss of contrast problems for this loss, but this is not really important for today. Okay, so how do you do style transfers for very large images? Well, when you have an image that is too large, what can you do? Actually, the naive solution is, well, you cut it into pieces. Right? And so what can we do with that? Well, the VGG19 features, it's a CNN, so it's invariant bar translation mostly, except for boundaries. And so you can actually cut into pieces, okay? And so that's what actually we do. And when you do that, you are able to compute the features of the network block by block. Once you have a block, you can actually stack its contribution to the gram matrix or the mean of the features and the standard deviation of the features. And so once you have done that, you are actually able to compute the style transfer loss block by block. Okay, so it's just, you have to wait more. But it's actually a roadblock here because it's cool to have the loss, but that's not what you want. What you want is a gradient with respect to the image of the loss, okay? And once you have cut block by block, you cannot simply apply autodiff and get the gradient of this loss because the computational graph has been lost. So how do we do that? So computing the gradient of the style transfer loss requires backpropagation through the VGG19 features that are really too large to fit into the GPU memory. So here is actually our key contribution, is that we observe that once you know the global statistics, the feature loss gradient is actually local. So this is true for all the terms of our loss, but maybe for now, let us focus just on the gram loss, okay? So the gram loss, once you compute the gradient with respect to the features of the gram loss, you get this. So it's just the local features V multiplied by the difference between the gram matrix and the target gram matrix. Okay. So this is a local term, and this is a global term that needs to be known in advance. But thanks to all these expressions, we're actually able to compute the local value of the gradient by backpropagating through locally computed VGG19 features. So this is a bit technical, but in the end, this is our algorithm. It has two steps. The first step is that, okay, we need to compute these global statistics. Okay, so we will cut the image into blocks, and we'll look over all the blocks and put them just in a forward way through the VGG19 to stack the VGG features of each block. And then we are able at this step to compute the global statistics, so the gram matrices, mean of the features, and so on. And once we have done that, then we can do a second loop. So we have to compute twice the VGG features because they have been lost. And so now for our new block, we will pass through the VGG19. Each of the features will be put in regard with its true local gradient thanks to the formulas I just showed you. Okay, and because now at the second step, we know the global statistics for the full image. And we're able to backpropagate this. And when we backpropagate this, we obtain a gradient image that has the size of the block. But actually, the center of this image is exactly the piece of gradient we would like to compute. Okay? So the takeaway message is that this procedure enables to compute exactly the gradient of the style transfer loss for images that do not fit into the GPU memory. Okay, so now let us look at some results. So here again, the releases by Van Gogh. Here is a picture from the south of France. And here is our results. Okay, so the resolution is 6,000 by 8,000 pixels. So let me show you some close-up details. All these tiny squares I did are already 800 by 800. Okay, so this is, and you can see that they really look like as if, well, they have a painting feeling, right? And it's actually what we were really looking for. Here's another example by Van Gogh. Actually, I think this one you can see at the National Gallery. I really advise to go. And another picture of landscape. And so here I will show you the different scales. Okay, so what we go course to find, we use 4 scales. And you can see this is actually the quality of the original paper by Gatiss. And here we increase the scale by a factor 2 each time. And let me show you some close-up. So what we found out is that actually this multi-scale algorithm is quite stable. And after the first transfer, we will only add fine textural details. And it's really coherent, so it's not moving so much. And these details are really crucial to convey this painting feeling, okay, of the final results. And actually, it is so stable that we exploit this to accelerate our algorithm because this is quite computationally heavy. And so our baseline where we will apply 300 iterations of the gradient-based optimization technique. It's called LBFGS, so it's a Casimir-Newton method. But since actually there is not so much difference from one step to the other, we found experimentally that we can actually decrease the number of iterations from one scale to the other and have decent results and the speed up by a factor 5. Okay. So, well, of course, we were not the first one to propose a style transfer for very large images. And actually, there has been a lot of work on making the Gatiss algorithms go faster. And we are actually on the opposite side. We wanted the best quality, and we are really, really long in computation. But let us compare with the methods that allow very high resolution style transfer. So the first one, and actually the best, is collaborative distillation by Wang et al. And this is an extension of a universal style transfer approach where they would use lighter CNN using distillation to replace VDG19 and its decoders. So this is a method that is quite fast, and this is a feed-forward neural network. Okay, but it's not multi-scale. And a second method is called URST for ultra-resolution style transfer by Chen et al. And it was more recent, but typically they cut the content image into patches and propose some normalization layers. But their approach of the problem is quite different, and actually they always resize the style image to a size 1000. So there is a mismatch between content and style, so you can never actually reproduce pen stroke details with this method. So it's not really convenient for our approach. Well, here is an example. This is not Van Gogh, this is Cézanne. And this is a Montagne Sainte-Victoire. So Cézanne likes Montagne Sainte-Victoire. This is a true picture of Montagne Sainte-Victoire. And here you have our result. So this is like 3000 by 4000 image. Here is the result by causative distillation that is not so good because there is no more Montagne Sainte-Victoire. And here is the result by URST, where you can probably see some problems by when you cut things into patches, you have to blend that seamlessly. It's not perfect. Okay. Well, in terms of comparison, this is always a bit subjective style transfer. Okay, so what we propose in this work is actually a simple method for qualitative evaluation that is what we call identity test. So this is actually a stupid task, but it's to highlight the artifacts of the method and to see how faithful they are to the style of the image. And so what we ask the algorithm is we give it, for the content, we give it exactly the same picture of the paintings. Okay, so we use the content and the style image, the same image, and apply the algorithm and see what happens. And so here you have the original image, here, this is our results. This is the result of collaborative distillation and URST. And so you can see that our result is quite faithful, but not as sharp, because we do a multi-scale way, so some details are not exactly the same. For collaborative distillation, you see that you have a bit of color blending that is not perfect. And for this other method, you can even see here patch boundaries that are visible, so it's not really accurate. So the good thing with this approach is that now you have you know what result you want, and you can you have aligned images, so we can use standard metrics like ESNR, SSIM, LPIPS to evaluate which method is more faithful to the picture. And we were the best for all the metrics, except obviously for computation time, because our method typically takes 25 minutes with a 5 times speedup for the fast alternative, whereas the others are just a few seconds. Okay. But also to evaluate the results, we conducted a standard perceptual study where we asked participants to choose their favorite results, both for identity tests, and also for style transfer. And here you have the results of this perceptual study. So basically, for maybe what is more interesting for today is the style transfer, and we were for style transfer, our method is favored by 90% of the votes. So we were quite happy, not surprised, but quite happy with the results. And to conclude, also let me say that originally the method by Gattis was not proposed for style transfer, but also for texture synthesis. And obviously, this is the same loss, and our approach is valid for very high resolution texture synthesis. And probably this can also be of interest for the community. But the difference here is that you initialize the image with a white noise, and so you would need to. So it's like the content image is a white noise, and there is no content there. And what you need to do is to use more and lot more scales to forget this white noise initialization. Because if you use only 3 scales, like for style transfer, you still see the low frequency of the white noise inside the texture. If you use more scales, you have really something really faithful to the original. It's actually pretty good results. Okay, so our main contributions with this work is that we introduced a 2-step algorithm to compute the style transfer loss gradient for ultra-high resolution images that do not fit in the GPU memory using localized neural feature calculations. And with this, we are able to synthesize images up to actually 20K squares if you have 80 gigabytes of memory. And in comparison with fast methods, where we show that we produce better results, but also maybe we can say that actually current fast methods produce images with too much artifact, I would say. And so for us, fast, high-quality style transfer remains an open problem to this date. And this is among our future works. Hopefully, we could come up with fast architectures to reproduce our results, and maybe also extend these ideas to other domains like videos or radiance fields. Okay. Thank you for your attention.